Deep underground in a stretch of central California most people have never heard of, instruments buried more than 2 kilometers into the earth have been picking up something that does not behave like a normal earthquake. It does not snap. It does not release its energy in a violent burst the way the ground usually does when a fault breaks. Instead, it creeps. It hums. It slips forward in slow, silent pulses that can last for hours or days, sometimes registering on seismometers only as a faint buzzing signature that looks nothing like the sharp spike of a typical quake. Scientists call it tremor, and for years it was thought to be something that only happened at volcanoes or along the deep subduction zones of the Pacific Northwest and Japan. Then, researchers found it happening directly beneath California's San Andreas Fault, and in the years since, as more instruments have gone into the ground and more data has piled up, the signal has only gotten stranger, more frequent, and harder to fully explain. This is not a story about a coming apocalypse, and it is not a story about some hidden government secret. It is a story about what happens when scientists get a new kind of window into the deep earth and start seeing activity nobody had properly documented before. Today we are going to walk through exactly what that strange signal is, why it matters so much for one of the most dangerous fault systems on the planet, and what it means for the tens of millions of people who live directly on top of it. Drop a comment and tell me if you have ever felt an earthquake in California, however small. A rolling shake, a sudden jolt, dishes rattling in a cupboard. I want to know where you were and what it felt like. If you want to keep up with everything coming out of the San Andreas system as new research lands, subscribe now. It costs nothing, and a thumbs up helps this reach more people who live in earthquake country and genuinely need to understand this. Let's get into it. To understand why this signal caught the attention of seismologists, you have to understand what an ordinary earthquake looks like on an instrument. A fault stays locked. Stress builds for years or decades. Then, in a fraction of a second, the rock breaks and the two sides of the fault lurch violently past each other. On a seismometer, that shows up as a sharp, high-frequency spike, over almost as fast as it starts. That is the earthquake signature that has defined seismology for more than a century. What researchers monitoring the central section of the San Andreas Fault near the town of Parkfields began noticing was different. Buried instruments were catching long bursts of low-amplitude vibration, sometimes lasting 15 to 20 minutes, sometimes recurring in clusters over several days, with none of the sharp onset of a normal quake. The energy was real, the ground was moving, but it was moving in a way that looked almost nothing like a rupture. At first, some of this activity was mistaken for background noise or dismissed as the kind of low-level rumble you might expect near a fault that is known to creep slowly at the surface. But as monitoring networks improved and more sensitive borehole instruments were lowered into the ground, the pattern became too consistent to ignore. This wasn't noise. It was a real, repeatable phenomenon made up of what scientists eventually classified as non-volcanic tremor. Deep, low-frequency seismic energy generated far below the surface, in the same general depth range where the fault transitions from a brittle zone that snaps to a warmer, more ductile zone that bends. The tremor bursts were clustering specifically around the boundary between the section of the San Andreas that creeps quietly and the section that stays locked and accumulates stress for a big rupture. That location is not a coincidence. It sits close to where the fault has produced some of its most significant historical earthquakes, and it sits uncomfortably close to the stretch of the fault that has not ruptured in a major way for well over a century. Let's slow down and actually explain what this kind of signal represents, because the word tremor gets thrown around loosely and it's worth being precise. Ordinary earthquakes are what seismologists call brittle failure. Rock breaks, two blocks slide past each other in a rapid, frictional slip. The whole event, even for a massive magnitude 8 earthquake, is usually over in well under a minute. Tremor is different. It is thought to be generated by slow, sustained slip happening deeper in the crust, in rock that is hot enough and under enough pressure that it does not snap the way shallow rock does. Instead of breaking all at once, the rock deforms gradually, releasing energy in small, repeated pulses rather than one dramatic rupture. Picture the difference between snapping a dry twig and slowly bending a green branch until it creaks. Both release energy, only one does it violently. This kind of slow, creeping deformation had been documented for years along subduction zones, the enormous fault systems where one tectonic plate dives beneath another, like the boundary off the coast of Washington, Oregon, and British Columbia, and the megathrust fault beneath Japan. In those settings, tremor is often paired with what is called a slow slip event, a period lasting days or weeks where a section of the fault slips far more than normal, but so gradually that it produces no damaging shaking at all. It is, in effect, a silent earthquake, one that releases stress on the fault without any of the violence of a normal rupture. Finding that same basic behavior on a strike-slip fault like the San Andreas, where two plates grind horizontally past each other rather than one diving beneath the other, was not something most seismologists expected. It suggested that the deep root of California's most famous fault was behaving in ways that did not fit neatly into the existing textbook model, and that there might be a whole layer of activity happening below the part of the fault we can actually see and measure at the surface. Why does this matter so much? Because tremor and slow slip are believed to interact with the locked brittle section of a fault sitting just above them. When the deep section slips, even slowly and quietly, it transfers additional stress onto the shallower, locked portion of the fault where big, damaging earthquakes actually happen. In some subduction zone settings, scientists have observed periods of intensified tremor followed, sometimes within days or weeks, by significant earthquakes nearby. The relationship is not simple, and it is not something that lets anyone predict an exact date, but it has raised a serious question that researchers are still working through. Is the deep, slow behavior of the San Andreas quietly loading stress onto the very sections of the fault that are already overdue for a major rupture? This strange deep signal did not appear in isolation. It surfaced at almost exactly the same time that a separate and much broader research effort was delivering its own unsettling conclusion about the San Andreas system as a whole. A team of researchers built a detailed physics-based computer model simulating roughly 1,000 years of earthquake history along the southern San Andreas Fault and its neighboring San Jacinto Fault. They fed the model everything available: radiocarbon-dated evidence of past ground rupture, records of historical shaking, and decades of GPS measurements tracking how fast the two sides of the fault are creeping past each other. Then they ran the simulation forward to see where the accumulated stress on these faults stands today, compared to any point across that entire 1,000-year window. The conclusion was stark. Stress on multiple segments of the fault system is now sitting at or above the highest levels the model produced anywhere across a millennium of simulated history. In plain terms, the fault is not gradually approaching some dangerous threshold sometime in the future. According to this research, it has already reached it. Here is why that number is so large. The southern section of the San Andreas Fault last ruptured in a major way back in 1857 in what is known as the Fort Tejon earthquake, an event estimated at roughly magnitude 7.9. That was well over a century and a half ago. In the time since, the Pacific Plate and the North American Plate have continued grinding past each other along this boundary at a rate of a few centimeters a year, day after day, year after year, for more than 165 years, with no major release along that stretch. All of that accumulated motion has to go somewhere. Since the fault has not slipped in a large earthquake, the motion has instead been stored as stress in the surrounding rock, compressing and bending the crust tighter and tighter with each passing decade. The study also identified something that makes the danger more complicated than a single fault simply being overdue. The San Andreas and San Jacinto systems meet at a geographic junction not far northeast of Los Angeles, an area researchers describe as functioning like a kind of earthquake gate. Under the right conditions, a rupture starting on one fault can jump through this junction and continue onto the other, turning what might have been a contained event into a combined multi-fault earthquake stretching across a much wider region. According to the modeling, current stress levels on both fault systems are elevated enough and close enough to each other that this gate is effectively unlocked right now. A joint rupture crossing through that junction could produce an earthquake somewhere in the range of magnitude 7.4 to 7.8, threatening the Los Angeles Basin, San Bernardino, Riverside County, and the Coachella Valley simultaneously, rather than just a narrow corridor along a single fault line. Put the two pieces of research together, and you get a picture that is genuinely worth taking seriously without tipping into panic. On one hand, a broad, decade-spanning model says the shallow, brittle part of the fault is holding more stress than at any point in 1,000 years. On the other, targeted monitoring of the deep root of that same fault system is picking up unusual, poorly understood slow slip and tremor activity in exactly the depth range that feeds stress upward into the locked zone above it. Neither discovery by itself tells anyone when the next major earthquake will strike, but together they paint a picture of a fault system that is under sustained, historically unprecedented pressure, with an active, still mysterious process happening underneath it that scientists are only beginning to fully characterize. It is worth pausing here to be completely honest about the limits of this science, because it is easy for a story like this to slide into fear without any real substance behind it. Earthquake prediction, in the sense of naming a specific date, location, and magnitude ahead of time, remains beyond what current science can do, and virtually every reputable seismologist will tell you the same thing without hesitation. What researchers can do is assess probability over long stretches of time, the way an actuary assesses the odds of a car accident without knowing which specific driver will be in one. When a seismologist says stress on a fault segment is at a historic high, or that the odds of a major earthquake in a region over the next 30 years sit somewhere around 1 in 3, they are describing a statistical likelihood built from historical patterns, physical modeling, and measured deformation rates, not a countdown clock. This is exactly why the discovery of deep tremor beneath the San Andreas is scientifically exciting, rather than something anyone can turn into a forecast. If researchers can eventually establish a clear, reliable relationship between bursts of deep tremor activity and elevated short-term risk of a larger earthquake nearby, the way some scientists suspect may exist in certain subduction zone settings, it could eventually feed into short-term hazard advisories, the same general category as the temporary elevated warnings Japan issues after unusual seismic activity along its own trenches. But that relationship is still being studied, still being debated, and still far from settled. USC seismologist Ahmed El-Banna, who studies this fault system closely, has put the honest answer about timing about as plainly as it can be put. The next major rupture on the San Andreas could come today, in 10 years, or in 30. On the geological scale this fault operates on, none of those options are meaningfully different from each other. If there is one place on Earth where scientists have spent the most effort trying to catch the San Andreas in the act, it is Parkfield, a tiny community in Central California that sits almost directly on top of the fault. For decades, this stretch of the San Andreas has produced a strikingly regular sequence of moderate earthquakes, magnitude 6 or so, that seem to repeat on a fairly predictable schedule through much of the 20th century. That apparent regularity led to one of the most ambitious experiments in the history of earthquake science. Starting in the 1980s, researchers installed one of the densest concentrations of seismic and geodetic instruments anywhere on the planet directly around Parkfield, in the hope of finally catching a moderate earthquake in the act, recording everything before, during, and after it in extraordinary detail. The expected earthquake was projected to arrive sometime around the early 1990s, based on the historical pattern. It didn't. The fault stayed quiet for over a decade past the expected window, a humbling reminder that even a fault segment with a seemingly clean, repeating history can defy the pattern scientists thought they understood. When a magnitude 6 earthquake finally did strike Parkfield in 2004, it arrived without the clear, predictable warning signs many researchers had hoped to find, despite years of dense instrumentation sitting in wait. It was this same stretch of fault and the intensive monitoring network built around it that later helped researchers first identify the deep tremor signals now generating so much interest. In a strange way, the greatest lesson of Parkfield was not that scientists learned to predict the fault. It was that the deep root of the San Andreas turned out to be doing something nobody had properly instrumented for in the first place. And that discovery only became possible because of the dense sensor network built to chase a prediction that never quite worked out. It is tempting when a story like this breaks to compare it directly to the two extremes the world has already watched play out. Earlier this year, Venezuela was struck by a catastrophic earthquake sequence along the boundary between the Caribbean and South American plates, a shallow, violent rupture that devastated communities living in unreinforced buildings, with a death toll that climbed into the thousands, and casualty estimates from international agencies running dramatically higher. Around the same period, Japan absorbed a magnitude 7.4 earthquake off its northeastern coast, powerful enough to trigger tsunami warnings and evacuation orders for tens of thousands of people. Yet the final toll came down to 2 minor injuries and no deaths. Same general category of earthquake, wildly different outcomes because of decades of difference in building codes, early warning infrastructure, and public preparedness culture. California sits somewhere between those two extremes, and it's worth being specific about what that actually means. On the positive side, the state has some of the strongest building codes in the country for new construction, and it operates Shake Alert, an earthquake early warning system built by the United States Geological Survey that can give populated areas anywhere from a few seconds to tens of seconds of warning before the most damaging shaking arrives, by detecting the fast, low-energy waves that travel ahead of the slower, destructive ones. That warning window sounds small, but it is enough time for people to drop and take cover, for surgeons to pause a procedure, for trains to begin braking, and for elevators to stop at the nearest floor and open their doors, all of which meaningfully reduces injuries and casualties in a real event. On the more concerning side, retrofitting older buildings has moved slowly, particularly the soft-story apartment buildings built across the state in the 1960s and 70s that are known to be especially vulnerable to collapse in strong shaking. Funding for emergency preparedness in lower-income communities remains inconsistent, and there is still a significant gap between what scientists understand about the risk sitting beneath Southern California and what the general public actually grasps about it. Japan's low casualty count from its own magnitude 7.4 event did not come from luck. It came from generations of sustained investment, public education, and repeated drilling that turned earthquake response into something closer to physical memory. California has made real progress in that direction, but the work is nowhere close to finished, and the discovery of unusual deep activity beneath one of its most dangerous fault systems is exactly the kind of finding that should accelerate that work rather than simply generate anxious headlines. None of this means the ground is about to open up tomorrow, and it is worth resisting the instinct, which spreads fast online anytime unusual geological activity makes the news, to treat every new finding as evidence of an imminent catastrophe. Earth produces earthquakes constantly. Thousands of small ones happen every single day around the world, and moderate ones in the magnitude 6 range occur roughly once every 3 days somewhere on the planet. Deep tremor and slow slip activity, once researchers started specifically looking for it, has turned out to be a fairly common feature of many fault systems worldwide, not some unprecedented anomaly confined to a single stretch of California. The reason this particular signal is getting attention now is not that it appeared out of nowhere. It is that better instruments finally made it possible to see something that was very likely happening quietly for a very long time in exactly the part of the crust that feeds stress into a fault segment already sitting at a historic high. That combination, a genuinely overdue fault segment, a documented record stress level going back 1,000 years, and a newly characterized deep process that may be actively loading additional stress onto it, is what separates this from ordinary background seismic noise. It is not proof of an imminent rupture. It is a legitimate reason for scientists to keep close watch, and a legitimate reason for the public living above this fault system to take preparedness seriously, rather than treating the big one as a distant hypothetical or a piece of Hollywood mythology. Information without action tends to curdle into anxiety, so let's end with what is actually within your control if you live anywhere near this fault system, or any active seismic zone for that matter. You cannot retrofit an old apartment building yourself, and you cannot change the deep physics of a fault 2 kilometers beneath the surface, but you can put together 72 hours of emergency supplies, water, non-perishable food, a working flashlight, a first aid kit, and any medications you or your family depend on. You can locate your home's gas shutoff valve and know how to use it. You can secure heavy furniture and water heaters so they don't become falling hazards during strong shaking. You can put together a communication evacuation plan with your family for a scenario where mobile networks go down, since that is exactly what happened in Venezuela earlier this year, cutting families off from each other for hours during the most critical period of the emergency. You can download the app connected to California's Shake Alert system so you actually receive those precious seconds of warning when they matter most. None of this takes more than an afternoon, and all of it is the difference between weathering a major earthquake and being caught completely unprepared by one. Step back far enough, and the story beneath California fits into something larger that is playing out across the planet right now. Scientists everywhere are getting better instruments, denser sensor networks, and longer historical records. And every time they do, they are finding that the deep Earth is more active, more complex, and more interconnected than older, sparser data ever revealed. It happened with the discovery of deep tremor along subduction zones over the past 2 decades. It is happening again as researchers map out exactly how much of that same behavior exists beneath a major strike-slip fault like the San Andreas. Better data does not usually make a hazard picture calmer. It tends to reveal more of the machinery that was always there, quietly working just below the resolution of the instruments available at the time. That is really what this story is about. Not a sudden, mysterious new threat appearing overnight, but scientists finally getting a clear enough view into the deep root of one of the most consequential fault systems on the planet to see a process that had likely been running for a very long time, entirely unnoticed. The San Andreas has not changed. What has changed is how much of it we can actually see. And that new visibility is arriving at almost exactly the moment independent research says the fault's shallow, dangerous zone is holding more stress than at any point in the past 1,000 years. Nobody can tell you when the next major earthquake will hit Southern California. Nobody honest will try. What the research community can tell you is that the fault sitting beneath one of the most densely populated regions in the country is under record pressure, that something unusual and only partly understood is happening in the depths that feed that pressure, and that the gap between what the science knows and what the public understands is exactly the space where preparedness either gets built or gets neglected. Japan closed that gap over generations, and it showed in April when a 7.4 earthquake killed nobody. Venezuela did not close that gap, and the world saw the cost of that in June. California is still writing its own version of that story, and the strange signal now being tracked deep beneath the San Andreas is one more reason that story deserves real attention right now, rather than after the ground finally moves. We'll keep following this as new research comes out. Every update on the deep tremor monitoring, every new stress model, every shift in how scientists talk about the risk along this fault. Subscribe so you don't miss it, and drop a comment letting me know where you were the last time you felt the ground move, however small the shake. These are not just abstract geological processes happening in rock nobody will ever see. They are events that reach directly into people's homes, and understanding them is how we stay ready instead of caught off guard. See you in the next one.